Hello everyone, my name is Atikur Rahman and I am a graduate student at UALR. My department is Physics and Astronomy. I have been working on mostly material science, how to synthesize nanomaterials, and what are the characteristics of those nanoparticles, and finally, what are the possible application of those nanoparticles. That's what we do in our lab. And today I want to show you my work at this Creative Expo. The title of my project is Synthesis of Selenium Nanoneedles for Solar Cells and Photocells. So in this project we will see how we can synthesize nanoneedles and how they grow and how we can change the size and shape of those nanoneedles. So we use laser technology to synthesize those selenium nanoneedles. Basically, what we did is we shine a bulk material, bulk selenium pellet with laser beam, and this is a pulse laser, and we synthesize the nanoneedles in the solvent. Solvent, it could be dye water, it could be ethanol, any organic or inorganic solvent. So we put the bulk pellet inside the solvent, and we heat that bulk element with the laser, and the nanoparticles synthesized inside the solvent, and we store those nano particles in the solvent so that it cannot be exposed in the outside environment. Here we tried different solvents. So in this first part, if you see these SEM images, we wanted to see what is the influence of the solvent. We used 6 different solvents here. In the right side, we wanted to see how we can change the shape and size of those nanoparticles. So in the right side, this is the influence of the repetition rate of the laser, which means if we increase the frequency of the beam, what happened. And then in the lower part, lower left, is the chemical identification. What are those elements? Is it really selenium, or is it a different thing? Or is it pure selenium, or selenium oxide? Those kind of thing. And after that, in the right lower right corner, this is the diameter and aspect ratio of those nano particles or nanoneedles. Here we plot the graph of repetition rate versus diameter, and repetition rate versus the aspect ratio of those nanoneedles. So the first thing is the influence of the solvent. You can see this is the dye water. This is ethanol, hexane, methanol, toluene, and acetone. So we keep the synthesis protocol exactly same. We use different solvents to see how in what solvent what type of nanoparticles we get. For dye water, we only get spherical shaped nanoparticles, and for the other solvent, we get the nanoneedles, and those are the organic solvents. And after that, we choose acetone to check the influence of the repetition rate. So in this right side, we have everything done in acetone. So we synthesize those nanoneedles in acetone, but this time we change the frequency of the laser. How many laser beam are hitting during the synthesis protocol. And you can see from first image, you see this is 100 hertz, and then 1,000, 5,000, 10,000, 15,000, and the maximum we can use in our laser is 19.9 kilohertz, so 19,900 hertz. So if we change the frequency, let's say if we increase the frequency, you can see those nanoneedles get very sharp, sharper and sharper and longer too. So the diameter decreases and the length of the nanoneedles increases and the tip of the nanoneedles get sharper, and that's what we plot here in repetition rate versus diameter. You can see the diameter is decreasing and the aspect ratio of the nanoneedles is increasing. And the chemical identification, so we use the Rahman spectra, and you can see from this graph we got trigonal phase and amorphous phase of those nanoneedles. Some of them are trigonal, some of them are amorphous. So we get the amorphous nanoparticles when we use the DI water, but if the other solvent, we get the trigonal phase nanoneedles. And also the color of those nano needles, you can see this is the kind of pink color, and the other are in gray color. So pink, those color nanoparticles, those solvents, those nanoneedles are amorphous phase, and in the gray color, those amorphous phase nanoneedles, those turned into the trigonal phase nanoneedles. And also we checked in the, you can see from the inset of those ACM images, this is the Tyndall effect of the nano particles or nanoneedles. So when we shine the laser beam in the colloidal solution, you can see there's the reflection, the refraction of those of the laser beam, and we can say yes, we have the nano particles inside the colloidal solution. This is the confirmation that we have the nano particles inside the solvent. And also we can check the color of the solvent. Some of them are pink, some of them are gray. So usually pink means you will get the amorphous nanoneedles, and for gray color it is trigonal. So what we can use, where we can use those nanoneedles. So our first application could be the solar cells and photocells, because the selenium has those optical properties, and we're thinking selenium nanoneedles will be a great candidate for the solar cell and photocell applications. So yeah, that was my work, and I'm very happy to present my work at this Expo. Thank you.